So, okay, let me start by just, I think, I'm not sure, actually, maybe I could have checked the lecture, but I might have said something slightly incorrect last time. So one thing I said which was correct was that by studying the conformal bootstrap equations, which we could write, which we could understand as saying that we have some positive coefficient times some vector space. It's an infinite dimensional vector space. I can always consider a subspace of that vector space by taking just 2 or 3 of the conformal bootstrap equations. And I can write, for example, in a 2-dimensional example that we can draw here very well, we can draw the direction of these vectors and see whether it's possible at all to satisfy this equation. If all vectors are pointing in the same direction, more or less, because the coefficients are positive, I cannot add them up to 0. And then, what we saw is that we could establish that there ought to be an epsilon, there ought to be a dimension smaller than some critical epsilon. So there was some critical dimension, delta epsilon critical, and there ought to be an epsilon somewhere before that critical dimension. Okay? So that's an upper bound. There's no lower bound. I think maybe I said that epsilon cannot be here, but that's not true. So what is true? I'm not sure if I said it, but if I said it, it's incorrect. So what I should say is that epsilon must be somewhere before this yellow stuff. Epsilon cannot be here. Why? Because if epsilon is here, then it means that because epsilon by definition is the smallest guy, it means that everyone is in this yellow part. Right? So if epsilon is in the yellow part, everyone is. Because everyone else is after epsilon. Then all vectors are pointing in this direction and it's impossible. But epsilon can be here, no problem, because if epsilon is here, no one forbids me to put other scalars here that will compensate and make sure that we can satisfy the equations. Right? Is it clear? I just want to make that point. So what we know is that someone must be here. It doesn't need to be epsilon. Epsilon can be here, or can be here. Someone must be here for sure in this part so that the equations can add up to 0. So, but the only thing we can say is that epsilon cannot be here because if it is here, everyone else is here, and then we cannot have a solution. Yeah? Is it clear? So it's one bound, it's not 2 bounds. Okay. Did I say it was 2 bounds? I don't remember. Okay, you also don't remember? Okay. Was it clear? Okay, very good. So here I just listed not what we are going to do next, but what we are not going to do. So this is a couple of things that we left out. So this was a crash course introduction to conformal field theory. If you are interested in learning more, here are something you might want to Google. Okay? So we did not discuss some very important object, a stress tensor, and the fact that in a CFT it is traceless. We did not discuss word identities, Weil anomalies, central charge, these theorems about RG flow. The embedding formalism, we explored it a little bit in the exercise. I told you it is something very powerful because it transforms the conformal group into Lorentz transformations, but we did not use it much. Operators with spin, you are going to play a bit with them in your homework to start seeing how the correlation functions look like. Conformal blocks, we discussed them, but not from a modern point of view of differential equations. We discussed conformal field theories. Together with supersymmetry, they form what is known as super conformal field theories, which are very important theories, very interesting theories. In particular, one very important one is n equals 4 super Young Mill. That one we will see later in this course, in the 3rd week. There is a very useful way of thinking about conformal amplitudes using Mellin amplitudes, in the same way that scattering amplitudes in a field theory look very natural in momentum space. That's where you always draw Feynman diagrams and so on. You could ask, is there an analog of momentum space for a conformal field theory? Okay? So what's the natural thing you want to do? It's not Fourier transform with respect to positions, because positions are not invariant under conformal transformations, but maybe do something like a Fourier transform with respect to cross ratios. And indeed, that's roughly what these Mellin amplitudes are. They are something that people started playing with 1 or 2 years ago, and they are Fourier transforms in conformal field theories with respect to cross ratios, or rather logarithm of cross ratios. And then there is a huge world of 2-dimensional conformal field theory, because in 2D the conformal group is very, very powerful, and there is a lot to be said about. And then there are many, many things that are particular to 2D that would deserve a course by itself. Okay, so today we change gears a bit and go, and we will start motivating AdS CFT, this duality between some gauge theories and some string theories. So the goal for this week, by the end of this week, I want to arrive at the duality, and more than have a duality between two theories. When we have a duality between two theories, the duality is useful if we have a dictionary. How to use stuff from one theory and get predictions for the other theory and vice versa. So my goal at the end of the week is to have arrived, motivated the duality. Of course, it's a conjecture. So what we will do is present a sequence of poorly motivated evidence for the conjecture and a sequence of hand-waving arguments that by itself, each of them is crappy, but as a whole, maybe you will find it convincing or not. But even though it's a conjecture, it's true. I mean, there is no doubt that it's true, because the kind of checks that are done of this conjecture from independent computation of both sides, you literally have to believe in winning the lottery like 3 times a day to believe that it could be a coincidence. So there are checks which are so tremendously convincing that only someone insane will dare think that a conjecture could not be true. So it's a true conjecture, but it's a conjecture, so it's impossible to motivate that A implies B implies C implies C, voila, AdS CFT. That's not possible to do. I cannot do that. So what I can do is present lots of evidence, lots of arguments, that there might be a dual. If it's a dual, it should be this one, and so on. And I think at the end you will probably be convinced, but okay, you will tell me by the end of the week. So by the end of the week, I want to arrive at this conjecture and tell you that the anomalous dimensions that are very important in conformal field theory, we saw, these deltas, they are the simplest object in a conformal field theory, they are mapped to the energies of the strings in AdS. Okay? Another very natural concept in AdS. We have strings, they have some energy, and the energy of the strings is the dimensions of the operators in the CFT. Here's one example of one. To establish a dictionary, we need to map many more things. But right now, the goal, my goal is to tell you about this particular point in the dictionary. Okay, we start with some claim, and the claim is that gauge theories, so gauge theories, like the theory that describes chromodynamics, that describes gluons, gauge theories with a large number of colors have a dual description in terms of string theories. It's a very general statement. So let's motivate this. So what I want to motivate is the statement that string theory emerges as a dual description of gauge theories with a large number of colors. And actually, to see how this goes about, and this is something that actually I know that there was an exercise by François David on exploring the large n limit of gauge theories, where you are asked to start drawing the diagrams and seeing how the diagrams look like. And this is a statement that diagrams in large n gauge theories organize themselves exactly in the same way that a string scattering amplitude organizes itself as a cartoon. The diagrams separate themselves into graphs of different topology that describe a string with no handles, a string with one handle, a string with two handles, and so on, as we will see. So we start with the simplest possible gauge theory because it illustrates already everything we need. The simplest possible gauge theory is a gauge theory in 0 dimensions. Right? Nothing simpler. Gauge theories in 0 dimensions are also called matrix models. So these are very simple theories. So they are 0 dimensions. So an expectation value in this theory is just an integral over matrices M, e to the minus, and then the kinetic term, I believe I want to normalize it like this, but I'll check my notes in a minute. Trace of M squared plus some potential V of M dot 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 divided by the same partition function without the dot dot dot. Okay, so this is the definition of my where V of M, don't copy yet because I'm going to check normalizations. V of M is some potential. which can be, for example, just, I don't know, t cubed, I don't know if I'll put over 3, I'll check again, m cubed plus t4 m to the 4 plus dot, dot, dot. Okay, let me check now. Okay, I normalized it like this. And I put the 2 here. Okay, very good. So this is a theory. You see, the kinetic term has no derivative because we are in 0 dimension, so that there is no space. There's just a matrix M, and we just integrate over matrices M. This M, we take it, let's take it to be Hermitian. And in that case, the measure that we use to integrate over the M is just, we integrate up to n. N is the number of the size of the matrix, so it's a Hermitian matrix of size n times n, and we integrate from 1 to n the diagonal elements of the matrix, mii, and then we integrate the off-diagonal elements, real part mij, product the imaginary part of mij, I smaller than j. Okay? An Hermitian matrix, the off-diagonal elements do not need to be real, but they are conjugates, so it's enough to integrate over I smaller than j. So this is the definition of a matrix model. Matrix model is this theory, this is the action, and we compute average of operators in this way. Okay? You see that this action is invariant, so there is a symmetry. This is what we call a gauge symmetry. Even though here, okay, gauge and not gauge is the same because the space-time is 0 dimensional, so there is one point. So to have a symmetry at each point or to have a symmetry at the only point that exists is the same thing. But okay, we have a symmetry, and the symmetry is just, we can multiply a matrix by some m, u, m minus 1, and that, of course, leaves this invariant because the trace is cyclic. So the trace transforms to u times whatever is in the trace times u minus 1. Yes?
By 0 dimensional, so do you mean that there's no time and space?
There's no time or space.
Oh, but then what is the matrix? What are the integers of the matrix? Or how should I? Why a matrix then? Or
a gauge theory is a theory where you have your fields are matrices, right? But furthermore, they depend on x and t. Right? So here I'm saying it's 0 dimensional, so they have no dependence on either x or t. Right? So just a usual theory. So normally we have nc equals 3 in real life. Here we have nc to be general, and we treat nc to be a large parameter. Yes?
Could you give some background about what theory means? What is theory?
What this theory means?
Yeah, like what does this theory represent?
As I said, this theory is what you would write if you would be asked to write a gauge theory in 0 dimension. If you want, forget about the first part. This is the definition. A matrix model is defined like this. Expectation values in a matrix model. What do I need to give you a theory? I need to tell you how to compute expectation values. I give you an action, and then you do a path integral with that action. Here I'm telling you, here is the action. Compute expectation value by integrating over the matrix, except that now this integral is not something fancy like a functional integral. It is literally just an integral over this n squared variable.
So, like, I mean, what is the physical thing? I just want to know what physical thing does this.
Maybe what you want to ask is, where do matrix models appear in physics, right? Okay, so they appear in many, many problems of discretizing geometries, of they appear if you want to study many statistical models on random surfaces. They describe random surfaces. But the reason why I'm using the matrix models and not a general gauge theory. I could use a general gauge theory. It's because all I want to pay attention to is the counting of powers of n. So I want to draw propagators and see how the powers of n organize. So I don't want to carry behind me, with me, space dependence. So it is just because space dependence does not play any role in the arguments that I'm going to give. But all arguments that I'm going to give apply if instead of m squared, you use the mdm. Just use some normal kinetic term. And then it works in the same way if you use QCD with a large number of colors. Just the mathematics of this model will be simpler, and it will illustrate all the physics that is important, which all comes purely from the counting of powers of n. Okay? But okay, if you are interested, it's actually a very beautiful subject, matrix models. I could make us like 1 or 2 lectures on physical applications of matrix models, but my motivation for this lecture is just to use it as a toy model for usual gauge theories, which are theories that also contain kinetic derivatives in the kinetic term. But those derivatives don't play any role in the argument, so it just simplifies my life to just drop them and to consider a matrix model. Right? Of course, if I have to motivate a lot of matrix model, maybe this was a bad idea, but I'm assuming it's okay not to motivate it much. Okay. So, let me remind you of just some basic stuff about, should I remind you a bit about Wick's theorem, or that's way too basic? I should not. That's maybe a bit too painful. So, okay. Does someone think I should? No? No one thinks I should. Very good. So then, what we can, so given this action, which is a simple quadratic action, I could compute the propagator, the average of Mij mkl. Again, everyone would know how to compute this propagator, right? Just write the action, write out explicitly what trace of m squared means with indices. It's a Gaussian integral, you can just compute. Is it clear? Okay, so here is what you get, and tell me if this looks natural or if you want me to do it a bit slower. You get G string, because it's the inverse of the kinetic term, it contains 1 over G string, and then you get delta IL, delta JK. And typically people get a bit confused that the first index is contracted with the last, and the second is with the first, but if you work out, it's exactly how it comes out. And if you did your exercise with François, you saw that this is, and actually it's the only way it could be. And this propagator, we draw it in the following way. We choose to draw it as a double line, as a fat line notation, where we have some I going to K and some J going to L, and the arrows keep track of who was the first index and who was the last index in the matrix. Okay? And again, so to answer your question, if this was a gauge field, right, this matrix structure would be the same. There would be here divided by x minus y squared, right, the positions. And here it will be the same, and there will be a point x and a point y, and there will be 1 over x minus y squared. But if at the end I'm not caring about the space dependence and just on counting powers of n that come from contractions, I don't need to care about that. Okay? So it is just to simplify my life. So for example, trace of m to the 4, let's compute this expectation value. Or let's compute the expectation value of 1 over G string trace m to the 4. I'm normalizing 1 over G string because you see in the action I normalize the vertices to come with 1 over G string times trace of m to the 4. This would be what naturally would appear if you would bring down one vertex, for example, in computing, say, some free energy, for example. And this would be what? So this is the expectation value. Let's write out very explicitly. What does trace of m to the 4 means? It means the following. Sum over I, J, K, L. M, you multiply 3 matrices, I, J, J, K, K, L, L, I. Right? And then you start weak contract them. You can weak contract these guys and these guys, or you can contract these guys and these guys, and so on. So this is one option, this is another option, and so on. And you get the following. You get that there is a sum over I, J, K, L twice the average of M, I, J, M, J, K times M, K, L, M, L, I. So this is the first case. And there is another case where you contract this guy and the last one, which is the same by cyclicity. So there is a factor of 2. Okay, this is just if I contract 2 neighbors. And then if I contract guys that are not neighbors, I get plus Mij Mkl with Mjk Mli. Okay? And then I just use what these guys give. So this just gives G string. And now you see the first delta function gives delta Ik, and the second gives delta Jj. And here we get delta Ki delta Ll times G string. Whereas here, we don't get any delta function with the same index. Here we get the delta Il, delta Jk, and here delta Ji, delta Kl. So this guy gives n, this guy gives n, and then when I contract, these two guys here give another power of n. They first give delta I, and delta I is n. Okay, and there is here 1 over G string that I forgot. 1 over G string here. Whereas these guys, when I multiply them all together, if I did no mistake, this, when you multiply them all together, they give n. Okay, indeed, because this guy becomes JL, then becomes LK, then it becomes LL, and then it just gives n. So at the end of the day, what we get is G string times 2, or the G string, no, the G string, sorry, 1 second. Yeah, it looks okay. G string times 2n cubed plus n. Okay? Just a trivial computation. But what we notice is that if n is large, this term is much bigger than this second term. But let's have a look at how they look like. How do we draw this graph? So this vertex here, you would draw it in the following way. You would write m to the 4 as some vertex that has 4 legs. Okay? And you would keep track of indices. So let me write it here. So there is I, J, J, K, L, K, K, L, L, I, and a bunch of arrows that go from the operator to the operator. Okay, so this is how this vertex looks like. And how do these contractions look like? So this one, we contract two neighbors. So this graph is something like this. So this is just some infinity symbol. Whereas this graph here, we don't contract neighbors, we contract next to neighbors. So this graph here, we contract this one with this one and the other one. So we contract first this guy with this guy. Okay? And then we contract two guys that are not neighbors. So to contract them, we need to go below the other line. So if we think of this as being some piece of ribbon, what happens is that this guy I can put on a plane, and this guy I need 3 dimensions. I cannot draw it on just a plane. So this guy, more specifically, it can be drawn on a sphere. I can put it on a sphere. And this guy cannot be put on a sphere. It cannot be put on a sphere, but it actually can be put on another surface. It can be put on a torus. By the way, am I going too slowly? Because we had an exercise on this. Maybe it's a bit... do you feel I'm going a bit too slowly on this? No, it's okay? So it cannot be put on a sphere, but it can be put on a torus. So let's try to draw this picture where it is on the torus. So let's draw the torus. Let me draw this picture. So now I draw a torus. And then I should draw like this. Can you see what I'm drawing? So let me lift the screen. So you see, it can be drawn on a torus, however. Okay. And graphs that can be drawn on torus but not on sphere. So this is called a planar graph. And this graph is called a non-planar graph. Okay. And what happens is that planar graphs are more important. In the large n limit, they dominate over non-planar graphs. We see it on a simple example. In a few minutes, I will show it in the general case. But what we will see is that the graphs separate into different classes. Those that can be drawn on a sphere, those that can be drawn on a torus, those that can be drawn on a torus with 2 handles, double donuts, those that can be drawn on a torus with 3 handles, and so on. And they become less and less important with n. Okay? So let me consider, just before moving to this general analysis, another example. Suppose we want to consider the expectation value of now a product of 2 traces. Which graphically means the expectation value of now an operator like this, 2 operators like this. Okay? Which sometimes I use the following notation. But maybe I don't need to introduce it actually. Do I need to? Well, maybe I'll not introduce it. It's okay. Would be an expectation value of 2 such operators. And what kind of diagrams would we compute? So let's see. Let's draw these guys like this. Here is one of them. I just bend it a bit. Okay? So let's draw 3 diagrams. So the simplest one is you just connect the operators. Okay? Plus, then we could have more complicated ones which involve interactions from the action. So we could have an interaction like this, for example. Some cubic vertex interaction plus and then we could have also other terms that cannot be drawn on a plane. For example, something like this, and then here some exchange of some matrix. Some term like this. Okay? Plus Okay? So let's count, say, powers of G that contribute to this graph and this graph, just to see the difference, maybe. Okay? But let's just do these 2 examples. Let's count powers of G that come from here. Okay, so let's start. So we have 1 over G string. Now you have to pay attention, otherwise you will look at the blackboard, just see a bunch of factors, and the words will be missing. So 1 over G square comes from putting 2 operators. Each of them comes with 1 over G squared. Now let's see, we have 1, 2, 3, 4, 5, 6 propagators. And each propagator comes with G string. G string to the power 6. We have 1, 2 vertices. Each vertex comes with 1 over G string. And then we sum over this index here, so that gives 1 power of n. We sum over this index gives another power of n. We sum over this index another power of n, and the external one another power of n times n to the 4. Yeah? It's clear? And this is equal to n squared. I'll factor out n squared. And then, let's see what we get. We get how many powers remain? 2 powers of G string and 2 powers of n times G string times n squared. This is what we get. Is it clear? Now let's work out this one here. So can someone tell me? Please. 1 over G string squared from the 2 external guys. How many propagators? How many? How many propagators? 6. G string to the power 6. How many vertices? How many vertices this time? These guys don't count. This I already took them into account from being external. So these guys I count them as being external. So there are 2 internal vertices. And then how many powers? So this is exactly the same as here. Okay? Because the only thing that I did different is instead of uniting, I went through and united with the other line. So this is exactly the same. But what's interesting is when we count powers of n. So let's now count powers of n. Let's imagine this is the frame of a window and we are putting some glass here. So we follow this line. So it goes here, 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 and here, and it closes. So all this internal line here just counts 1 power of n and 1 other for the external. So the difference is that we only get n squared instead of n to the 4. So the only difference is that now this diagram gives n times G string squared, but without any n squared multiplying it. So this matches our expectation that non-planar graphs, like this one, are less important than planar graphs. Right? Now the picture is that if you will now start doing more and more and more and more diagrams, this would look more and more like some dense surface, and this would look more and more like some dense surface with 1 hole, and so on. So the picture is that these diagrams here, these planar graphs, they will describe, as you do more and more and more graphs, some string. Okay? They become a discretization of some surface. Okay? So I'm drawing some graphs. A bunch of planar graphs that can be drawn on the plane. Because these 2 guys are insertions, it will be like a cylinder. And you have a bunch of planar graphs that describe a string. And these guys here, as you sum them and take many, 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 they will start resembling like a string also, but with 1 handle, because you can draw them on a torus. So in the limit where you start putting more and more and more graphs, the intuition is that a string theory should emerge. But to claim that this is just a cartoon, so now we want to check that indeed these graphs come with the same powers of G string and of tooth coupling that in the very first lecture, when I was motivating of formal field theories, we had this cartoon for what a string scattering amplitude should be. And for how powers of G string should come about. Whenever I have a hole, I should have 1 more power of G string. And if I have 2 holes, 2 powers of G string, and so on. So that's what we want to understand. Yes?
But could there be worries about doing the expansion at all? Because then higher order diagrams will increase the order of n. So you can have like n to the... the more loops you have in a planar diagram, the more n's you will have. Isn't that problematic?
Very good. So that's a very good question. So how can it be? Because indeed, as you are pointing out, the more diagrams I have, the more powers of n I have. So what is going on? So the claim, we will see in a minute, you are already anticipating, is that all these graphs, the power of n is always n squared. The power of n is always n to the 0. But it's always n squared times a function of a parameter lambda times a function of lambda, where lambda is G string times n is kept fixed. and this is the 't Hooft expansion. It's an expansion where the coupling is going to 0, n is going to infinity, G string times n is fixed, and if it is, then you have a function of G string times n, but multiplying always n squared. You see, here we got n squared times lambda squared. This is one term. If you would consider the example above, we got, hopefully, n squared times G string only. You see? But the leading term is also goes like n squared times lambda. Okay, but that we will arrive at this slowly. Okay, we will now. That's what we are now going to conclude. So let's analyze the general n and G string dependence of any graph. Okay, so a graph contributes S. But since someone asked, let me emphasize once again that at this point, you see very clearly why all this discussion, the fact that you have some point at some position X and some point at some position Y or not, it's totally irrelevant. All we are doing is counting powers of N. So of course, it doesn't matter if this is, if here I put some point X and point Y, from the point of view of point powers of N, this is all irrelevant. So it was just to clean the discussion. So how does a graph contribute? So we have G string to the power of the number of propagators. Minus the number of internal vertices. Each vertex contributes with 1 over G. Minus the number of external vertices. Because external vertices we normalize in the same way as internal ones. In other words, we have here minus the total, we have in total minus the number of vertices. Okay, so someone, for example, was counting 4 here because he was counting internal and external. Okay, it's exactly what appears in there. And then, what do we have? And then we have n that appears with a power that is bigger and bigger as you go to more loops, as you were pointing out. So it's n to the power of the number of closed lines, closed color lines. Okay? Now, what is this from the point of view of the graph? The number of propagators is the number of edges of a graph. This is the number of vertices of the graph, we denote by V. And the number of closed lines is the number of faces, F. You see? Is the number of how many, if this is the frame of a window, and I put a glass of window here, a piece of glass here, and a piece of glass in the exterior. I need 3 faces. Here, okay, it will be some fancy glass, but it will be one single piece here and one single piece for the outside. It will be 2 faces. So then, what we have is the following. We can write this as okay. We can write this, but now we notice that E minus V minus the number of faces. So if you have number of edges minus number of vertices minus number of faces, this is a topological invariant. This is what is called the Euler characteristic. This is Euler's theorem. If you see the very first pages of any book in topology, they typically start by this formula, where this is the genus of the surface where the graph can be embedded in. Okay? So this here is the genus. So this is called the Euler characteristic chi. It was Euler's birthday yesterday. It's a good time to introduce this. It's a pity it was one day off. Yes? It's minus chi? Yeah, it's possible that it's minus chi, yeah. Okay. Euler deserves better than this, but okay. Maybe this is the definition of minus chi. Okay. Sorry. Okay. Does someone know? Is it chi or minus chi?
It's minus chi.
Minus chi? Okay, this is minus. But doesn't matter. What's important is that the genus appears in this way. So the bigger the genus is, the bigger the left-hand side, and so on. So there is a direct connection between the number between this and the graph where it can be embedded in. So, but we don't have G string to this power. We have G string with edges minus vertices. So what we have to do is divide and multiply by the number of faces. So just doing some trivial algebra of dividing and multiplying, what we get is the following. What we get is the following. We get that the average and expectation value will be equal to a sum over graphs that can be embedded in genus G times G string to the power 2G minus 2 times some function that depends on that genus G of lambda, where this function comes from the sum of all graphs of a given topology. Where lambda is G string times n. Okay? So what we have is, okay, there is some normalization when G string is, so what we have is some overall normalization, 1 over G string squared, and then we have planar graphs plus some graph with one handle times G string squared plus some guy with two handles times G string to the 4 plus dot dot dot. But this is exactly the cartoon that defines string theory. It's exactly the picture that we have for string theory, where we sum over surfaces, and the weight of the surface is given by powers of G string. You get one G string for splitting the string and one G string for merging it again. And here, one G string for splitting, one for joining, one for splitting, one for joining, 4 powers, and so on. Times the general function of lambda, you have to resum all graphs with a given topology to get the full result. So we see that we have some idea that G string, in this very cartoonish way, should be related to the string coupling that tells you if strings want to split or not. Okay? And lambda, which was G string times n, is related to the string tension. For a given, remember, for a given topology, we sum over all surfaces of a given shape. So this lambda is what controls how many graphs we need to sum and so on. It's related to the way the vibration of the string, whereas G string is related to how many times they are allowed to split. And we can consider processes when in the leading order only planar graphs contribute. Okay? So these are just the leading contribution. In the limit, in the large n limit, which is the limit, the n goes to 0, n goes to infinity, G string goes to 0 with n times G string fixed. And this is what's called the 't Hooft limit that was introduced by 't Hooft. Okay. Of course, this is equivalent to saying that we have a sum of n to the power 2 minus 2 genus times some f tilde g of lambda. Just I can divide them. I can complete the power that I need to get Euler characteristic either in n or in G string. The two expansions are totally equivalent. They just amount to redefining a bit our function f tilde. Right? I mean, in other words, I can multiply this by the corresponding power of n, multiply and divide, then I get this. So this f and this f tilde just differ by some lambda to some power of the genus. Right? It's just a different way of expanding. And this was related to your question, you see. Now when genus is 0, I get always n squared times a given function of the coupling. If genus is 1, I get no power of n times the function of the coupling. And this was exactly what we found. If genus is 1, we got n squared times the function of the coupling. Or we could write this in the other way, which is 1 over g string squared times n g string to the power 4. Just equivalent ways of writing. So anyway, either this times function of lambda or this times function of lambda. And indeed, this guy was n squared, and this guy was n to the 0, and it was genus 0 and genus 1. Very good. In particular, okay, if you have a correlation function, okay, of some connected correlation function, this will be of order n squared plus subleading. Okay? So G is equal to 0. Now this is for connected. All we said is for connected. We could think a bit about what it matters for disconnected. But I want to mention something that we already start seeing from this discussion, that in the gauge theory, so this is the gauge theory, and this is the string theory, we are already establishing kind of some duality between gauge theories and string theories. And you can ask, what object is dual to a single string? And the single string we see, which is just some loop that moves, this loop, the way of thinking of a loop, a natural way that comes out of this very general analysis, is that a nice way of thinking of a single string is to thinking of it as a single trace operator. Okay. The single trace operator, you can think of it as some string that is being emitted, it propagates, and it absorbs again. If I consider a three-point function of this kind, so a correlation function of trace m cubed 3 times, would correspond to the process where I have an interaction of 3 strings, because this would correspond to just drawing. Let me draw the single trace maybe like this to illustrate better that it looks like a string. You see? This is just identifying one operator, and then I have another operator here, and another operator here. And then all I do is connect them. And start drawing this lots of Feynman diagrams. And so on until it looks like some field surface. Okay. So there is this emergent picture that as you start from a gauge theory, you end up with some string theory. And if this can be drawn on the plane, the string theory has no holes. If there is some lines that cross, it means the string has one hole, and so on. Okay? So just with this very end-wavy arguments, we see that the gauge theory, there is a coupling, there is a tension, there is a single trace operator mapped to a single string. What's the most fundamental property of a single trace operator in a conformal field theory? Now let's suppose that we have, let's make a jump. This is kind of a jump. In a conformal, it's a conformal field theory, but it's also a gauge theory. So let's suppose we have a conformal gauge theory, a gauge theory that has conformal symbol. What is the most fundamental property of an operator in a conformal field theory? Or the only property of an operator in a conformal field theory? It's its dimension. Right? So then you could ask the dimension delta, what does it correspond to? Okay, and I can anticipate that the nicest quantity you can have for a single object is the energy of this string. This is the answer, but I just want to open a parenthesis. We will arrive there in a more rigorous way, but there are not too many things that it could be. Okay, very good. Then let's try to build a bit more on this intuition to see if this is working out okay. Because if we are, say, a scattering of 4 strings, the easiest thing for the strings to do is to just one string propagate somewhere, the other string propagate somewhere else, and not talk to each other at all. So we should see this notion that when we start computing correlation functions, if this picture is correct, to leading order, they want to be disconnected. If you want to consider three operators going to 3 operators, if they are strings, the leading order process should be when the strings propagate without interacting with each other. Interactions should be more suppressed. It's just physics, right? Yes?
I mean, in the gauge theory, how much take the truth limit and...
Okay, in the gauge theory, so okay, again, this is, I want to give you an appetizer. I'm not deriving anything. I will, of course, derive this very carefully. In the gauge theory, there will be some coupling. That will be, normally we call G and Mills. And there is some number of colors, NC. And then we take the combination G and Mills squared times NC to be constant.
Well, is there any physical argument?
It is what I just gave. If you take this limit, the graphs in your gauge theory organize as an expansion of a string, so it's a natural limit to take.
Why should take? In case you get this.
Sorry?
I mean, except you get this expression, does it correspond to any physical presence? We can take it too.
Okay. So then your question is, suppose we have some gauge theory which has 3 colors, right? Not n, which is infinite. That's 3. 3 is not very big. Now, what I can tell you is that in this limit, when the number of colors goes to infinity, there is a huge simplification. The theory becomes much simpler. The class of diagrams you have to compute are just planar diagrams, and you get this dual description in terms of a string. So it's a huge technical improvement. You can compute much better. And the corrections are 1 over n squared, which are for even if n is equal to 3. If you ignore the fact that n is not very large, even for realistic gauge theories, it would already give you some approximation with like 10% to physical observables, if you consider that n is large. So even in physical theories, often, what you can do is consider a large n expansion. Even if n is 3 or 4 or 5, you treat it as a parameter that is very large and you expand on it. Okay? It's less crazy than epsilon expansion, where you expand from epsilon from 4 to 2, right? I mean, here at least it's 1 over 3 squared. It's 9. It's 1 over 9. At least it's reasonably small. But it's actually very good. It turns out that this expansion is very good. It works very well. And it predicts most of the phenomenology of mesons, baryons, and so on, just with these very hand-waving arguments of saying who could interact more with who based on just counting powers of n. It explains a huge amount of phenomenology. It's really extremely good as a physical approximation. The other thing I could say is that if you have a gauge theory and try to see how do couplings change when I run my renormalization group. How do couplings flow? And if you compute the beta function, you see that the beta function for a theory, a Young-Mills theory with coupling G, involves n on the right-hand side. You compute the beta function, it depends on n. So that means that as you renormalize your G, it gets renormalized in an n-dependent way. So, and what happens very nicely is that if you consider the beta function not for G, but for lambda, for the 't Hooft coupling, the beta function for lambda is n-independent. It only depends on lambda. So the theory wants to be described in terms of lambda. Even if you start, it flows naturally. What flows naturally is lambda. So it's very natural to take this limit. but the main motivation is that, first of all, it is a technical simplification over a general quantum field theory. Only planar graphs dominate, so it is one simplification. And it's a simplification where a string theory description emerges. So we get a new tool for studying gauge theories. We don't have that many tools. Whenever we get a new tool, we should be very excited. In some theories, furthermore, taking large n limits can be something very physical. Taking crazy limits when this n goes to infinity or to 0 or even to complex values can be something relevant physically, sometimes in statistical physics. There are limits where taking crazy limits in n is equivalent to studying percolation and physical processes as well. But that's a different direction. I think it doesn't. My answer doesn't satisfy you. Maybe you can ask me at the end. It's my impression that you are not convinced. Okay. Anyway, so let's try to see. To make this picture even more compelling, let's try to see that indeed our intuition, which is the intuition that if you consider a propagation of, say, 3 or 4 strings to leading order, they just propagate untouched independently of each other, is correct. Okay, yes?
When you draw the string, it doesn't seem to refer to the fact that we started with external vertices with 3 legs. Does the string perhaps also contain the 4 point? So when you, for example, say the string there, the discretization gives us the Feynman diagrams, right? And
This
you
one
specifically use 3 points.
I use 3 points to denote the external legs, yeah.
But so does that mean that the picture also entails the 4 point and the 5?
If I would consider trace of n to the 4, it will be a 4-point scattering up.
So there's nothing in the picture that reminds us it's 3 instead of 4.
Yeah, you could color the external vertices red. You could put some blue here indicating that these guys are external. Everything else is internal, so this is a 2-point function. So you have to put some operators that describe inserting a string, okay, that correspond to inserting the string, and then you have all the diagrams that describe the discretization of the string. So in string theory, putting these operators is the analog of putting vertex operators that you have to put in string theory. And you put vertex operators as a way of inserting your string. Okay, there was another question, I think, there, right? You had a question? No? Okay, so now what we want to see is this intuition that if you have some string theory, to leading order, of course, when I consider a process with 4 strings, what will the strings do if I consider some evolution of strings? To leading order, they just evolve untouched. So this is what happens first, plus, and then they start interacting. Right? This is just some obvious physics. So this should be more important than this. Right? So this should be the leading contribution. And this should be subleading. So let's see how this comes about. So what we are saying is that if we consider a correlation function, can I write here? Can you read right here? Or should I go there? Now I started here. Can I continue? If I consider a correlation function of 4 operators, indeed, what happens is that there is a disconnected contribution plus a connected part. Okay. But now if we see the disconnected contribution, each of them goes like n squared, right? Because this is the disconnected, but of course it's connected by definition. This goes like n squared, whereas this guy goes like n squared. Right? So immediately we see indeed these guys are indeed leading. And this equation here, this statement, is what is called the large n factorization. Is the statement that to leading order, a correlation function just decouples into 2. So it likes to decouple because as soon as you decouple, you get extra faces in your Feynman diagram. So as soon as you decouple as soon as you split, you get more faces, you get extra powers of n. So graphs, combinatorically, they like to decouple. And this physical is the statement that strings like to evolve without interacting. It's much better. Okay? So we have that O connected is of order n squared. Everything that is connected is of order n squared. So it's better to break into smaller pieces. But now we notice something interesting, that if we consider a correlation function of 3 operators, okay, a connected 3-point function, okay, So this picture is checked. Now I'm moving further to a slightly more refined interpretation of this check. I'm saying that if we start with a connected guy, of course you could complain, you could say, wait, we emphasized very clearly that 3-point functions by themselves are not physical quantities. I defined my operators by putting a 1 over g string outside. Why don't I put 5 instead of 1 over g string? Then it would change this power counting. Right? It will depend on the normalization. So let's do it properly, and let's say that we consider the 2-point function, and we raise this to the power 3/2. Then it's normalization independent. Okay? So then, this guy, if you do, it scales like 1 over n, because each guy scales like n squared. Similarly, the correlation function, O connected, divided by O connected to the power 4 over 2, which is also known as 2, goes like 1 over n squared. Okay? So what these guys are doing, static disconnect, is measuring the strength of the string interactions. It is measuring its connected diagram, so it's measuring this interaction, the 4-point connected guy. And the 3-point connected is measuring the 3-point interaction. Okay? So this is measuring the interaction. Okay? On the other hand, if we imagine what kind of powers, what kind of interaction should we get in string theory, say in the limit where strings can be approximately described by a field theory. Okay? So string theory contains gravity. So in particular, it contains gravitons. Right? So what do we expect, for example, for the interactions between 3 and 4 gravitons? Well, let's see. So for example, if we have, let's try to go to this limit of string theory where we have this gravity. So I remind you that string theory contains gravitons. And then we expect to get 1 over g Newton times some integral d dx of the fields. So, what we get is the following. If we have an interaction of some particle, some 3-particle interaction, okay? If we divide it by the normalization of this guy to the power 3/2, again to make it physical, the normalization, we expect this to go as, if you work out exactly the same kind of analysis, square root of g Newton. And if you do it for a 4-point interaction, if you divide this by the disconnected part, this goes as g Newton. And you conclude that g Newton is indeed, that measures the interaction, is indeed identifiable with the n, which is 1 over n squared, as it should be. Okay, this is more, and now that I'm writing it, I'm realizing that it's not so crucial to have this explanation, but okay, it is a true statement. So what I want to summarize is the following. We have gauge theories. So I want to emphasize an important point, is that everything would go through. Okay, so let me emphasize here in a box. So if all this analysis, trace of m squared, would be replaced by something in space-time, nothing will change. It would, I mean, one thing would change. It will make the answer to your question a bit simpler. How do we identify the external ones? The external ones will have positions, x1, x2, x3, whereas the other one, they are integrated. It will be a bit more helpful to identify who is external and who is internal. But otherwise, from the point of view of counting of powers, everything is the same. So we see that gauge theories in a limit of large n they organize themselves exactly as string theories do. There are the planar graphs that contribute to leading order. Then there are the subleading and so on, which tell us that a string to leading order just propagates without splitting and joining again, which costs, it's a more quantum process. So to leading order, in this 2th limit, we only click planar diagrams where strings don't split and join. Then we see that strings, if you have more than one string propagated, if you have many strings propagating, they want to propagate to be just free strings. And then interacting strings. And free strings dominate, which is just a statement that in this large n limit we want to have boundaries. So disconnected diagrams dominate over connected diagrams. So we have, in the large n limit, we have free strings. And then we start having interactions. But don't be fooled by this name. Free does not necessarily mean trivial. By free string, I mean a string that does not interact, but it vibrates. You still have to sum over the shape of this string. Right? It vibrates. You sum all diagrams with this topology. It's not the same as a free theory. A free string is something interesting. So it's a free string. There is no G string. There is no interaction. But there is still the quantum vibrations of the string. And we see that the interactions between strings are given by, are governed by this n or G string. Alternatively, I can exchange it by G string by absorbing powers of lambda. But indeed, they are suppressed. This is nothing. This is roughly the same statement as this one here. Okay, very good. Of course, just with this kind of cartoons, this is not going to be the way that we are going to be very constructive, right? I mean, just with these cartoons, now I cannot just say, therefore, theory A is dual to string theory B. Because what these cartoons serve is to say that we should expect a string theory description of a gauge theory. Now, which exact string theory it is, what are the details, what's the action of this string, and so on, of course, these cartoons are manifestly insufficient to answer that. So that's why I'm saying that I'm going to give you many arguments that each of them by themselves is not convincing. So this one should convince you that if you have a gauge theory with a large number of colors, there should be a string theory. It should tell you that G string should be related to the coupling, lambda to the tension, single traces are related to single strings, and so on. But this is more or less what it does. So tomorrow we switch to another argument more based on string theory, where we'll start playing more with brains and understanding dynamics of brains. Did you see brains in the string theory course at all? Did you discuss brains and the low energy dynamics of brains? Did you say that open strings end on brains? And did you say that open strings describe the low energy dynamics of brains? You can think as open strings as the degrees of freedom of the brain that describe the fluctuations of the brain and so on. Not that much. Okay. I will have to think. Okay, let's continue tomorrow. There are two questions before we.
This gauge string duality exists for both open and closed strings, or only for closed strings?
It's for both open and closed strings. It's for both open and closed strings. Yes. But this question is better posed after tomorrow, probably, where people can make sense of what exactly you want to know. There was another question.
So, what does the free string to the power of 3 over 2 mean? Or what does that mean? I mean, so if the free string...
No, this just means normalize the 2-point functions to 1. Then an interaction will come with power of G string. And if you normalize this is just telling that properly normalized fields, their coupling is governed by G Newton, which is what we know, right? Gravity couples to G Newton. That's what governs the coupling of gravity. So if you want to identify G Newton to the way operators are being coupled, we should identify G Newton with N. That's all it says. This ratio is just to emphasize that whenever you want to learn what's the coupling of fields, be careful that you should normalize things properly. You should not make normalization dependent statements. That's all it means.
And is there a square in the denominators? I mean, for the last graph.
A square in the denominator? No, I think it should be okay.
I mean, I tried to compare this one to that one, and there is a split.
Right. Yeah, I don't know exactly what I mean by this. This means probably the interaction. Well, let me just, yeah, this blackboard, there is some chance that there are something incorrect here. So let me just say that 3 graviton interaction, a 3-point interaction will be governed by G Newton, and a 4-point by G Newton. This is a true statement, but what exactly these cartoons mean, I don't remember. Maybe it means propagator, maybe it means, I don't remember what I meant by this picture, so let me just say this, which is correct for sure. More questions? Is it clear? Was it too fast? Okay? Okay, very good. See you tomorrow.